So we're very happy to have Saumya Sinha today with us. She's an assistant professor in the Industrial and Systems Engineering Department at the University of Minnesota Twin Cities. And before joining Minnesota in fall 2022, she was a postdoctoral scholar at Rice University and then a visiting postdoctoral fellow at the Houston Methodist Hospital, where she was working in the areas of optimization and organ transplant. Before that, she received her PhD in applied mathematics at the University of Washington in Seattle, where her dissertation focused on robust dynamic programming. So her research in general focuses on decision-making in uncertain and dynamic environment, and especially motivated by applications in clinical decision-making, healthcare, and health policy. Please.
Thank you so much for the introduction, Sylvia. Thank you for the invitation. Looking forward to talking to you all. I'll be talking about some work I had done with actually 2 undergrads at Rice when I was a postdoc. This works from a couple of years ago. I have given this talk before, so if it is repetitive for some of you, hopefully you'll find value in the repetition. And yeah, this work is kind of early results. I think there is a lot to be said about where this can be taken, where it goes. So I hope we'll be able to have some of those conversations towards the end. Okay, so let's start with just what is a multi-objective optimization? Where does it show up? As the name suggests, we are trying to simultaneously optimize multiple objectives over a common set of decision variables and constraints. And with applications in multiple domains, as you can imagine, wherever you may have different priorities that often conflict or compete with each other. So for instance, if you're working in inventory management, you may be trying to balance cost minimization with some kind of service level maximization. In clinical decision making, this shows up in treatment planning. So if we're trying to optimize a radiation therapy dosage to maximize the tumor control, but also trying to control any side effects that come to the healthy tissue. In power systems, this shows up when you are trying to balance cost and environmental impacts and reliability of the power supply. So generally, wherever you have multiple priorities that may lead to different optimal solutions, multi-objective optimization is one way to think of those problems. I will be focusing on multi-objective linear optimization and with discrete integrality constraints. So let me start with just what a general multi-objective LP looks like. So now instead of one objective, I have k linear objectives, and my feasible region still looks like a standard polytope in Rn in this instance. I have non-negative linear constraints, non-negative variables, but I have k objectives instead of just one. So every feasible point is being mapped to a vector in Rk instead of being mapped to a scalar. I will represent this as a matrix. So I'll have instead of a cost vector, I have a cost matrix, which now has k rows corresponding to my k objectives. And still the feasible region looks like that. Okay, so to envision why we need different solution methods, techniques for multi-objective optimization, let's look at this picture where I have 2 objectives. Let's say F1 increasing along my x-axis, F2 increasing along my y-axis. And let's imagine these 2 solutions, y1 and y2. Now, y1 is better with respect to F1, but has a lower objective value of F2. Y2 exhibits the opposite behavior. So in general, as far as their objective values are concerned, these 2 solutions are not comparable. And that is the fundamental challenge with multi-objective optimization, that you will have a suite of solutions that are not comparable to each other. If you just wanted one solution to a multi-objective problem, just take any weighted combination of your objectives and you're done. So generally what we're looking for is the entire set of such solutions that are mutually incomparable, which I'll call the non-dominated set for this problem. So generally we are trying to find the entire non-dominated set. And then in multi-objective linear programming, it has been shown that every point on this non-dominated set can be obtained through some linear combination of the objectives. So I do have multiple objectives, but if I had a way of sweeping over every possible linear combination, I would recover this entire set. Okay, so that's for multi-objective linear programming. Now, if I add integrality to the mix, so I still have a matrix with k rows. My objective function is mapping vectors, points in Rn to vectors in Rk. And I'm now additionally assuming that my feasible regions are all integer. Then you can imagine I still have a polytope, but my feasible images are going to be some lattice or some discrete points inside this region. Okay, and then now I can still talk about all non-dominated or mutually incomparable images. As you can see in this particular illustration, I have 3 of them. And because of this non-convex nature of my feasible image set, I will characterize my solutions in 2 categories. If I look at the convex hull of my image set, these 2 points sit on the convex hull, whereas this little point over here, it sits strictly inside the boundary of the convex hull. So points that are on the convex hull are called supported. They're supported by the convex hull. Points that sit inside the convex hull are called unsupported or non-supported solutions. And everything that's on the convex hull is kind of like the linear case. So a solution is supported if and only if this image can be obtained through a weighted combination of the objectives. Something that is sitting in here that cannot be obtained by a combination of the objectives, so more specialized techniques are required. Once again, so if you just needed to find one solution, it's easy. Take one combination of the objectives, you'll find one solution. But we are generally after the entire set of solutions, which is where the problem gets challenging and interesting. Okay, so the research question when we started this project, it was just about duality for these problems. So very simple theoretical question of how do we define a dual for a multi-objective integer program? And then of course the follow-up with what was the point of it? So can we use it to inform something about solution techniques for MOIPs? What I'll present is a partial answer to question 2 as we get there from the answer to question 1. Our main results are that we defined Lagrangian relaxations and a Lagrangian dual for a multi-objective integer program and analyze the behavior, strength, and so on of that dual. We also develop a super additive dual, which I'm not going to be able to talk about in 25 minutes, but the paper talks about it if you're interested in that. One of the key findings that's sort of the germ for, I think, any future research that we do over here is that in the single objective IP case, the convex hull relaxation is the gold standard. And we found that because the convex hull relaxation is not going to be tight at these unsupported points, Lagrangian relaxations can actually yield tighter bounds. I'll show a picture to illustrate what I mean by all of that. And so then our next question was, can we try to characterize the extent to which Lagrangian relaxations can improve upon convex hull bounds? Okay, so just starting off with the definition of relaxation, as you can imagine, it will be very simple. It will be a direct extension of an intuitive definition of Lagrangian relaxation, just like from single objective integer programming. But we need to do one thing before that. So even in terms of defining a relaxation, right? So if you think back to your integer programming class, we talked about a relaxation as some other problem. If I'm solving a maximization, my relaxation is going to give me an upper bound on the optimal value of my original problem. Now, that's easy to do when I have one optimal value, when it's a scalar. Now, my optimal set, my non-dominated set, is a set of points in Rk. These points are mutually incomparable. We don't know how many such points there are going to be. So what we need is to define a way of comparing sets of non-dominated points, because any relaxation is going to have a different non-dominated set. And how do we compare these two sets? So we came up with a definition, which I was very pleased with when we did, because I thought we were the first to implement. And then we found papers which had already done that. So it confirmed that we were on the right track, but it was not a novel contribution. Anyway, just visually what we mean, a set T is going to be larger than my set S if it sits inside this green shaded region. So it's really sitting on top as a set of my non-dominated set illustrated over here. Okay. Turns out this is a very natural definition that allows us to write the properties of our duals in very direct analogs of all single objective results, as we'll see. But to specify, to be specific, a k-objective problem is a relaxation of my original problem if its feasible region contains the feasible region of my original problem, and its ND set is now an upper bound on the ND, the non-dominated set of my original problem. So hopefully you're able to see that this is just a direct analog of how one would define a relaxation in single objective integer programming. Okay, so with that, the known relaxations that have already existed in the literature, again, very similar to single objective problems. The first is the linear relaxation. If I simply drop all integrality constraints, my non-dominated set would be this red line. As you can see, it is an upper bound on my primal, on my original problem's non-dominated set. And I can also talk about the convex hull relaxation, where I'm now going to recover the convex hull of my feasible image set, and that gives me this red line. The behavior of these things, these objects, is again, as we would expect. The linear relaxation is going to be weaker than the convex hull relaxation, and the convex hull relaxation is going to be tight at all the supported and non-dominated images. So what I mean by that, again, if I remember from the illustration, these three dots are the ones I'm trying to recover. As you can see, the two supported solutions, they coincide with the non-dominated set of my convex hull, but the one unsupported solution is going to lie strictly inside that relaxation. Okay. But yeah, so with that, we can define the Lagrangian relaxation, again, with direct analogs. Suppose I have some nice constraints and some complicating constraints. I will try to dualize the complicating constraints by adding a Lagrange multiplier. In this case, my multiplier, so normally if I was dualizing M1 constraints, I would have a vector of length M1. Now I have a matrix of multipliers corresponding to each row of my objective, but is still non-negative. And we can still show that with our definition of the bound sets, this problem is going to be a relaxation. And the quality of this relaxation is going to change from lambda to lambda, right? And then again, sticking with convention, the dual is defined as the best of all bounds from Lagrangian relaxations. So if I just take the non-dominated set for every relaxation, take the union and find the minimal region, the minimal points of that set, that would give me the tightest or the best bounds, the lowest bounds from all my Lagrangian relaxations. Except it turns out this way of defining the dual, while it's very reasonable and it'll give us some strong duality as we expect, mathematically, this dual is not something we will ever try to solve. And the reason for that is the dual problem now has a feasible region. So this set of values is non-convex, disconnected, neither open nor closed. We have an example that illustrates all of those properties. So any hope we might have of trying to formulate this dual problem as a nice multi-objective convex optimization problem is lost. So we can still look at it as an object, but what we will find is actually the relaxations are the right tool to do the analysis we were hoping to. Okay. All right, so just continuing with the duality theme, we find that weak duality will always hold. Strong duality holds at the supported solution. So the ones that are on the convex hull are sort of nice and easier. Strong duality holds under this condition, which is identical to the condition you have in single objective IP for Lagrangian duality. Now we start observing some more features about this, that not only is this dual strong, but if we try to find a lambda that makes this dual strong at a supported solution, we can actually find one that has at most one non-zero row. So even though we started off with K objectives, so my matrix was K cross M1, I only really need one of those rows to be non-zero. Everything else can be zero. And I can still find something that is strong at a supported solution. And then we have an analog of complementary slackness. Okay. And this condition is not sufficient for strong duality at unsupported solutions. So this Lagrangian dual Still, we cannot guarantee that it will be strong at unsupported solutions. So neither was the convex hull relaxation. The dual doesn't get us any further either. But then in an example, we observed something interesting that led to the questions we tried to answer. So far we have all of these duality results, which are new, but also direct analogs of everything we have seen in single objective IP. So it feels a little bit like an academic exercise, but we weren't too sure what the value of it is going to be in terms of solving the problem. And then we had an observation. So let's look at this image a little bit closely. Here, my yellow squares are the three non-dominated points that I'm after. I want a way of recovering all of them. My black solid line is the convex hull relaxation ND set. So as expected, it coincides at the supported points and it completely misses the unsupported one. My linear relaxation is this dotted line, which is even worse. Now, the non-dominated sets I get from Lagrangian relaxations, they change from set to set. So for instance, for a particular value of lambda, I recover these three blue circles, the blue dots, that coincide with the supported points and completely miss the unsupported one. For a different lambda, which corresponds to these orange dots, I am way off from the supported solutions and even from the unsupported one. But the interesting finding was that this point, this dot, actually sits below the convex hull relaxation. So that started us thinking on, can we use the Lagrangian relaxation to somehow get a tighter bound on this point, even if we cannot guarantee equality? So even if we don't know that there is some lambda that will recover exactly this point, can we get closer to it as compared to what the convex hull relaxation was being able to do? So that's where we were headed with this. In general, the Lagrangian dual and the convex hull sets are not going to be comparable to each other, but we have more hope with the relaxation. Okay, so that led us to, let's try to compare Lagrangian and convex hull bounds. So again, I'll try to illustrate all of this through pictures as much as I can. So now let me focus on a single non-dominated image. And I have a whole host of bounds that my convex hull, upper bounds that this convex hull relaxation is providing. And we want to see, can we find something using a Lagrangian relaxation that is better than these bounds? Turns out we can under some conditions, and those conditions are about which constraints are dualized. I won't spend too much time going into why this works, but to give you a flavor of what this looks like, we want to make sure that the right constraints are dualized so that there is room to explore in those directions that was not available when solving the problem. So we want to remove those constraints, add a penalty, and open that region up for exploration. So the right constraints being dualized, we define them in terms of the dual cone at this particular point. Think of it as we want room to explore in regions where all the objectives are improving. So we can sort of violate the constraint a little bit and still get away with it. So points that are in universally improving directions must be dualized. And then we illustrate that you may have a problem where that is not possible. So definitely this condition is not satisfied in all instances. But if it is, then it provides some guarantees about the performance of the Lagrangian relaxation. Okay, so if that result holds, then we show two things. First, given any convex hull bound, I can also find a Lagrangian relaxation. I can find a lambda that gives me the same bound. So the Lagrangian relaxations, if I look at all possible relaxations, they perform no worse than the convex hull bound. And under some additional assumptions on things like boundedness, we can show that there exists a Lagrangian relaxation that strictly improves upon a convex hull upper bound. So this indicates some promise that under this particular conditions, if I have the right kind of problem and I dualize the right kind of constraints, then the Lagrangian relaxation is going to give me tighter bounds. The main value of this is in solution methods, because just like the single objective IP, you have different kinds of branching and bounding techniques, which all depend on being able to find upper and lower bounds. Now, not just on a single point, but on the entire set of non-dominated points. And that's where we hope to go with this. Okay, so computational promise. This was just analytical observation so far. We wanted to see if there is any indication that this can be computationally helpful. What I'll present are very preliminary, naive results. As I said, I think this has just opened the door for us. We want to explore what the strength of this little observation can be. So how do we effectively leverage Lagrangian relaxations to get good bounds on my non-dominated set? But what I'll present is a very naive early result. So what we did is we solved a bunch of problems which use bound sets. Let me skip through some of that. Okay, I do need it. So in branch and bound for multi-objective IPs, what we are trying to do, as I said, is find a set that will provide an upper bound for the entire non-dominated set, and find a set of points that will provide a lower bound for my entire non-dominated set. This has led to the idea of bound sets, and historically, the linear relaxation and the convex hull relaxation, the non-dominated sets of those have been where people have gone looking for these upper bound sets. So I can try to solve the convex hull relaxation, and I know it will give me an upper bound on my non-dominated set, even if that upper bound is not tight at certain points. And we want to see if replacing that with the lower bound can be helpful. So the reason I say this was very naively done, we just did 100 random instances of small bi-objective problems, linear assignment and knapsack, one constraint that was dualized. We didn't try to do anything smart in finding the right lambdas. We just enumerated naively and compared. I'll spend time on the illustration and then skip over the results in the interest of time. But basically what we saw is different kinds of behavior are possible by just naively enumerating my lambdas. So think of these orange dots as an approximation to the Lagrangian dual, and the blue line is the convex hull bound set. As expected, the convex hull bound set completely captures my supported efficient points and completely misses my unsupported points. These are the black squares. Whereas my Lagrangian dual in this particular instance completely captures all of my non-dominated points, including the two non-dominated ones, two unsupported ones. In another instance where I'm trying to solve a bi-objective knapsack with a dualized constraint, again, as expected, the convex hull exactly recovers all the supported points and completely misses all the unsupported points. And at least through this approximate dual set, we find that some of the unsupported points are picked up by the relaxations, but some of them are not. This is not to say these would not have been. As I said, we did not explore the space of all possible lambdas. There's definitely more work to be done in that space, but some preliminary evidence over here. This is an example of one illustration. We did it over multiple random instances and recorded this and found something that the Lagrangian dual shows some promise. Superadditive dual, I'll skip away. So let me just talk about the takeaways. What we did was we formulated Lagrangian relaxations in dual for a multi-objective integer program and proved strong duality under some conditions that were very similar to conditions in the single objective case, and defined a superadditive dual, which I haven't talked about. Then we made an observation that the Lagrangian relaxations may give better bounds at unsupported solutions than the convex hull relaxation, and are no worse than the convex hull relaxation at supported solutions. So if we had a way of efficiently generating this an approximate Lagrangian dual set, it definitely has promise of being a better bound set, a tighter bound set than the convex hull provides. So these are the two papers. It's a selection of results from these two papers that you're welcome to look through and talk to me more about. Just one slide on where do I think this work is going. So I think the most important thing is how to incorporate this relaxation into solution algorithms and how to efficiently find good lambda values, because definitely enumerating over lambda is not a promising direction. We also had some observations where we noticed that the Lagrangian relaxation can be tight at unsupported solutions, whereas others where it doesn't quite attain equality. But we didn't find anything principled that would guide us towards when a Lagrangian dual is going to be tight at all the solutions. But I think there is hope that some kind of problem structure might provide insight, but nothing yet. Definitely interested in exploring that question. That's all I have to say. I think I'm at time, so I'll stop here for questions.
Thank you very much. Shall we move to the breakout room directly with the questions? What do you think, Alex? Or
Sure. We can do that that way. Saumya gets some more pointed technical questions.
exactly.
Thank you. Thank you everyone for attending. Even if you're not sticking around for the breakout rooms to ask questions, you can please feel free to stick around to just chat with us because it's also an opportunity for socialization. So grab your tea, grab your coffee, and a wine if you're in Europe. I don't know, and whatever you prefer, juice, and hope to see you there. But thank you for coming, and we'll see you also hopefully next month. We have another session of dots on May 2nd, I believe. Hope to see you then. Thank you for both speakers.